Okay, I guess we're at time. So as DKG said a minute ago, we have 1 hour today. The agenda is relatively full, so we'll try and scoot on through it. My name is Stephen Farrell. I'm one of your co-chairs,
and I'm Daniel Kahn-Gilmore, other co-chair.
And okay, so DKG, you can talk to these slides, and I'll shut up.
Sure. So this is the note well. We are well into the IETF. Hopefully you've seen this before. This covers rules about what is discussed in this meeting. Hopefully you've already read it. I think we'll skip to the next slide here. So the agenda is tight today, as Stephen mentioned. We are going to have a brief reprise of the strategy for the working group, how we're working on the documents, and then we have 3 presentations today. We have a talk about key extraction attacks through encrypted private key corruption, a discussion about the interoperability test suite, and using simple octet strings for elliptic curves. And then in the remaining time, we have opportunity for the editors of the crypto refresh draft, which in particular will be Paul today, to talk through the status of the draft and any issues. And hopefully by the end of this, we will be able to discuss an upcoming interim. I want to give folks a chance to look at this agenda and raise concerns. I see a note from Paul in the chat that says, am I talking today? We have a chance to go through open issues with the draft. I think we can just pull up the GitLab issue tracker and give people a chance to talk about it if we have the time. But I want to focus, the presentations that we have are going to consume most of the meeting. So any other agenda bashing, or shall we move on to a discussion of the overall plan, just so we're set on the same page? I'm not hearing anything. If something comes up and you want to agenda bash later, you can always just bring it up in Jabber. So just a brief reminder about how we're working with this. Before the group got rechartered, there was a lingering RFC 4880 BIS draft 10 that was from a previous iteration of the working group that failed to produce an RFC. In trying to figure out how we could get consensus on a new RFC that still meets the in-charter scope for the new revision of the working group, what we've done is we sort of reset to RFC 4880. We picked a new draft name. It's now draft IETF Openpgp Crypto Refresh. And we are trying to restore the changes that were in 4880 BIS-10 topic by topic. So each revision tries to address each one. So far we've had 3 revisions. 0.0 is basically 4880 with some minor formatting changes. 0.1 fixed all the published errata and added the Camellia cipher and updated some terminology, along with one change about whitespace that, thanks to the list, has been reverted. 0.2 included elliptic curves, merging in stuff from existing RFCs. We changed the registries to be specification required instead of IETF consensus or RFC required. We added SHA-3. We brought in curve 25519 for ECDH, and we deprecated some of the older stuff that people shouldn't be using anyway, and we reserved a bunch of code points for what had been in BIS-10. In the upcoming revision, I guess Paul can maybe speak to this later, but I think we're talking about staging ED-DSA and maybe V5 keys and V5 fingerprints in the next one upcoming. And thank you to everyone who's reviewed on the list for these changes. It has been really useful to get a sense of what the working group thinks about them. It's pretty clear that we will fix up some parts of it. I see Yoav's comment there about just how legacy the stuff is that we are trying to put in here. But yeah, it's 2021. Let's get OpenPGP up to date. So that's sort of the direction that the working group is going on. Next slide, Stephen. Just about the mechanisms, the mechanics for how we're doing it. So the draft is being developed in Git. We are using a central GitHub repository as a place to keep track of the changes. We're using gitlab.com. That is not github.com. In that repository, you will see 3 documents in Markdown form, which are the source, 4880.md is a markdown source version of what is the actual original 4880. 4880bis.md is a markdown version of 4880bis-10, that is the previous draft from the previous iteration of the working group. And crypto refresh is the draft that we are working on. So there are opportunities to do sort of diffs and comparisons between those three documents. As Paul mentioned in the chat, RFC diff is useful for comparing these things. I find actually also diff, given the markdown sources, is useful for comparing to the different documents. And if anybody wants to talk later, probably not in this group, but in a separate conversation, I'm happy to walk you through. If you're interested in trying to help edit or propose changes, I can help you with some of that. We were using the issue tracker where possible, but of course, all conversation goes on the mailing list. But when stuff comes up on the mailing list, we do like to keep track of it in the issue tracker so that it doesn't get lost. There's been a fair amount of discussion, which is much appreciated. I think that's it for the recap here. And if possible, I'd like to go ahead and get started with the next presentation, unless folks have questions.
So just on that, I think it's maybe worth emphasizing, since we're likely to do a lot of the kind of detailed issue tracking and processing via a set of interim meetings. And so there's probably a slightly larger group here today. It's probably worth emphasizing that we're not really in a position where the working group is open for fresh new ideas just now. Really what we're doing is we're playing kind of catch up on the set of diffs versus 4880 that we already nearly know for sure that we want to include, but we're making sure we get consensus on those before we go forward. So it's a slightly kind of bookkeeping exercise to some extent, but with technical parts. But the main thing is, if you have a super good idea for something new to do with PGP, now is not really the good time. By all means, drop them out to the list, but expect that we might say, let's get to that after we've already got a bit of success with the current work. Just want that to be clear.
Yep.
And if there's no questions on the plan, then we will move to key extraction. Let me just pull that up. Okay, Lara.
Hey.
Great. So just say next slide whenever you need it.
Yeah, sorry, there's okay, good. Hey, I'm Lara Brusagini. I am a security engineer at Protomail, and as part of my master thesis, I work with Kenny Patterson and Daniel Hoinghans, and we looked into the security of Openpgp. And one of the questions we are focused on is how far can an attacker go if they have access to the encrypted private key of the victim. So today I'll give a high-level overview of the attacks and issues that we have found, and then I will also discuss the countermeasures. Next slide, please. So in terms of the threat model we are considering, we have an attacker who has write access to the encrypted key. So this means that the attacker can corrupt the encrypted private key of the victim. And then the victim will use a key as long as they can decrypt it with their passphrase. In practice, this means that the victim will not check the key fingerprint before using the key. Next slide, please. So the requirement on key decryption is relevant because in Openpgp, the private key is not fully encrypted. So here you can see the schema of an RSA key, for instance. And when you encrypt the key, only the fields in gray are both encrypted and authenticated. So those include the secret key parameters. And if an attacker tampers with the encrypted data, then the key decryption will fail. But there are also some parameters that are stored in clear text. And in case of RSA, those are the public modulo N and the public exponent E. And if the attacker corrupts those values, then key decryption will work fine. And Climarosa in 2001 already noticed this partial integrity check issue, and they exploited it. They showed how an attacker could corrupt the public parameters of a DSA key. Then they wait for the victim to sign using the corrupted key. And from the faulty signature, they could extract the DSA secret exponent. Next slide, please. Now, at the time, Openpgp was not fixed to address that specific attack vector. So what we have found is we have looked at the same attack idea again, and we have found that it's not just DSA keys, but any key type is potentially vulnerable to this kind of key corruption attacks. Specifically, when it comes to faulty signature attacks, DSA, EDDSA, and RSA keys can be directly compromised, and the attacker needs to corrupt the key only once, and then it needs as little as one faulty signature to extract the secrets. But also, any encrypted curve key as well as Argamal key can be indirectly targeted by transforming the key into a DSA1. And this kind of key transformation is possible without breaking key decryption because all key types except for RSA have a compatible format of the encrypted data in a private key. Now, if you're not familiar with the key types, I'll just point out that ACDH keys and LGAMAL keys are encryption only. However, thanks to this key transformation, they can still be compromised using faulty signature attacks by converting those keys into DSA1s. So aside from these attacks that target signing, we've also found some attacks that exploit decryption, but those are a little bit more involved, and we will be sharing more information about the decryption attacks, as well as all the mathematical details of the signing attacks. Soon enough, we are finishing up a paper, and we will be publishing it and sharing it with the community soon. Next slide, please. So just to review what are the existing protocol level protections in place that are relevant for the attack. So as mentioned, the issue is that only some of the parameters are authenticated. This is either with AAD or CFB, but in both cases, the public values can be corrupted by the attacker, and key decryption will succeed. And when the attacker has control of the public values, it means that the attacker is also free to really replace the subkey binding signatures, for instance, to make sure that they still verify with the corrupted public key parameters. Now, what the attacker cannot do is forge third-party certifications, so those become invalid. And also, if the public fields are corrupted, then the key fingerprint necessarily changes. But to reiterate, that's why in our threat model, we really consider a user that is not careful enough and basically ends up using the key without inspecting the key fingerprint. Next slide, please. And so currently, if an Openpgp library wants to prevent key corruption attacks from happening, what it needs to do is to perform some kind of key validation after decrypting a private key and before using it for secret key operations. So specifically, the idea of key validation would be that since you have the secret values, the secret parameters that are necessarily authenticated, but you have the public values that are potentially corrupted, you want to make sure that the private and public parameters are consistent. And key validation is a bit of a delicate process because if you do it wrongly, it's either ineffective or it can open up the possibility of additional attacks. For instance, the validation method that does not work is trying to use the key, for instance, to sign and verify a message or encrypt and decrypt a message. So in many, depending on the key type, even if the operation is successful, you have no guarantee that the private and public parameters correspond or are strong enough. So instead, to carry out proper key validation, one should really check the mathematical relationship within the different parameters. And this means carrying out some algorithm-specific checks. And in case of RSA, these are straightforward enough. But this is not the case with all key types. Next slide, please. In fact, for instance, in LDML, there is no way to fully validate a key by checking the correspondence between parameters. So it's possible, but it's not feasible. For DSA and EDDSA, the operations are still expensive, and in the case of DSA, it's kind of tricky. And in general, what we've seen in practice, we have reviewed a number of popular Openpgp libraries, and none of them is safe against all of the attacks that we have found. So even if key validation is implemented, it's often missing some key checks. And in terms of end-to-end attacks, we have found 2 real-world applications that are vulnerable to these key corruption issues. So next slide, please. So in light of what we think is the seriousness of the issue and the fact that it's difficult and inefficient for implementations to address the problem, what we would propose is that the standard be changed so that key decryption fails if the public parameters are corrupted. And this can be achieved without introducing any new primitive in the spec. It can just reuse what libraries have already implemented. Specifically, if AED encrypted keys are standardized, then the idea for them would be to put the public parameters and the key type inside the associated data, which is data that is not encrypted but is still authenticated. Instead, if we remain with CFB encrypted keys, then one possibility is to put the public key and hash it together with the private one. Currently, in CFB keys, only the private parameters are hashed. And this second CFB solution is the same that was proposed in 2001 when back the first DSA attack was published. And so the advantage of this kind of protocol level solution would be security-wise that you don't delegate anything to the implementations, and you have a solution that works across all algorithms, and that is really much faster. So that's all for me.
Great, thank you. I guess we have time for a couple of questions. I'm sure one of them will be when can we expect to see the full detail, and where, or will you just let us know?
We're really reviewing the paper, so I don't want to give any time predictions, but it should be very soon.
Okay, if there are other questions, then if people would just like to get themselves raise their hand using the Meet Echo tool, and there's some chat in the Jabber that Kenny's been handling, I guess. Kirsty.
You for the presentation. You said you found 2 real-world apps where this was vulnerable. Did you report the vulnerability through their vulnerability disclosure program? Did you get in touch with the apps themselves? Thanks.
Yes. So both the libraries that we have reviewed and the applications have been contacted. And the application specifically have already been fixed already a few months ago, actually.
Great. So we don't seem to have. Oh, Kenny, are you in the?
Oh, just to say thanks. We did responsible disclosure, I guess is the short way of saying what Lara just said. And so all the affected libraries have been notified and have had a chance to patch. And as Lara already said, both of the applications we found to be vulnerable have fixed.
So I just wanted to say thanks to the researchers, to Lara and Kenny and your colleagues who worked on this for bringing this to the attention of the working group. It sounds like you did a pretty good review of existing implementations, but obviously there may be implementations that you don't know about. So being able to talk about it here should hopefully give people a chance to have a heads up if they have an implementation that they haven't published. So much appreciated for bringing that to the group.
Sure.
Yeah, indeed. I think it's really good work. Thank you. Okay, and you were exactly on time, so that's even better. Thank you for that too. So I think if we move on to the next one, it's Justice.
Hi, can you hear me?
Yeah.
Yes, we can hear you.
So just whenever you want next slide, just let me know and I'll click the button for you.
Great. So I'm Justus. I'm here to very briefly talk about my efforts to bring interop testing into the Openpgp community. If you're curious, you can find the results on tests.sequoiapgp.org, and the presentation is both in the IETF tool and will also be on our website. Next slide, please.
Justus, if you could be a little bit louder, that would be great.
Okay, I will try to make that happen. Better? Can you hear me better? Okay. So I've been an Openpgp developer for roughly 5 years. I started working for Werner on GNU-PG in 2015. And nowadays I'm employed by the PEP Foundation. And our mandate is not only to write a PGP implementation, although we did that. Our implementation is called Sequoia. Our mandate is also to improve the ecosystem as a whole. And writing an universally useful test suite has been on my mind for quite some time. In fact, I proposed to do that at the Openpgp conference in Cologne in 2016. Next slide, please. So why should we do that? So we needed our a way to verify our implementation, right? And if we have to do the work anyway, we can make it useful for others too. And this is in line with our mandate of improving the ecosystem. And it's good for other implementations too, because writing tests is a lot of work and they get free tests. And there are secondary effects too. So we hope that users will enjoy better software and increased interoperability. And recently I've learned that this will also help the standardization effort. So the working group can see what's implemented and maybe also see where the implementation is lacking or where implementers would benefit from more guidance. Next slide, please. So the tests are black box tests, and there are two kinds of tests. The first one I call consumer tests, where artifacts are produced by the test suite and then consumed by all the implementations. And the other kind are producer-consumer tests. And here the artifacts are also produced by the implementations being tested. So you get this nice interop matrix. And the test suite uses an interface called SOP, or the stateless Openpgp interface, that has been extracted by DKG. And you can see some examples. So here we generate a key, then we use it to encrypt some data. Data is read from standard in, and the ciphertext is produced on standard out. And to decrypt, you do the same. You feed the ciphertext on standard in and get the plaintext on standard out. And currently, the test suite just uses 5 very simple operations and gets out a lot of information that way. So on the right, you see an example test. Every test has a heading, and it has a stable link that you can refer to in bug reports. Then you get a description and maybe additional artifacts like certificates. And there is a little button next to artifacts. And if you have the right font, you also get this little magnifying glass in the button. And if you click on that, you get taken to a packet dumper to inspect the artifact. If you look at the results, you see check marks and cross marks. Check mark means the operation succeeded. Cross mark means it did not. And some tests have an expectation. So we expect an operation to succeed, or we expect an operation to fail. And if an implementation matches the expectation, it's marked as green and has an ear mark in the left top corner. And if it fails to meet the expectations, it's red and has a ear mark in the right top corner. Most tests start with a base case, so to make sure we are all on the same page. And then there are some variants. And some of the variants where the interpretation or the expectation is not clear, they don't have any expectations, so you get a kind of white row. And sometimes, mostly in producer-consumer tests, the producer fails to produce an artifact, or the produced artifact does not meet the expectations, so you can get a cross mark there too. Finally, if you hover with the mouse on cross marks or check marks, you can see additional output like the result of successful signature verifications or error messages. Next slide, please. So this is an example of an signature verification test. So Niebe started looking into encodings of ECC artifacts, and to aid that, I decided to write a test. And the test verifies an EDDSA signature, and it starts with the base case. That's green for all implementations except for GPT 1.4, which does not do ECC. And then you see a variant where the S value of the signature is 0 padded, and many implementations just support that, even though it's slightly out of spec. And then just for fun, I decided to tag the R value as well, and none of the implementations like that. Next slide, please. This is an example of a producer-consumer test. So, or maybe we should call it a scenario test. And this models key generation, encryption, and decryption. So you generate a key with implementation A, encrypt for that key with implementation B, and then decrypt it with the implementation A. And you can see GPGME, for example, using GPT 1.4 fails to pass that test for every implementation that creates an ECC key by default. And DKGPG generates an DSA and Elgamal encryption key, and some implementations do not support Elgamal, so that fails. Finally, key generation with GPT 1.4 is not supported. Next slide, please. So currently we have around 80 tests, and that amounts to around 400 test vectors, and I found at least 80 bugs and reported around 80 bugs across 9 different implementations. So I consider that a success, and we improved implementations across the board, not only Sequoia in accordance with our mandate, and we also improved the understanding of the ecosystem. So during our implementation effort, we asked us questions: how are implementation handling this or that? And we just wrote the test to find out. And there are some tests where the implementations vary wildly, and this may point out where implementers need more guidance. Next slide, please. So let's start with the good news. Algorithm support is excellent. So almost all implementations support almost all algorithms. And if you look at the chart on the right, a significant percentage of the points you see are the algorithm supporters. Then there are problems. For example, if you consider signature subpackets, it's unclear what implementations should do if there are multiple, maybe conflicting subpackets. There is uncertainty about what information you can take from unhashed subpacket areas and how you handle critical subpackets. Then timestamps are a bit of a disaster. It's sometimes not clear how to handle missing subpackets, missing timestamp subpackets. What to do if a signature's creation time is in the future? Or what if the signature's creation time predates the signing key's creation time? Or what if at the time the signature was supposedly created, the signature subkey was not bound or was revoked, or the certificate was for some reason not valid? And there are unknown packets. So I think unknown packets should be ignored as much as possible to ensure forward compatibility. Say you're verifying signatures, detached signatures, and there is a V4 and a V5 signature, and you don't dig the D5 signature. You should be fine with verifying the V4 signature. Expirations. Implementations vary wildly with respect to the question of, do signatures expire, like in the context of certificate component binding signatures? Do primary key binding signatures expire? And do certs expire? If you look at revocations, revocations are unfortunately not as reliable as we like. And then there is the question of, are there soft revocations? As in, if I revoke a user ID, but I join the organization later on again, can I rebind the user ID? There are tests looking at robustness. So certificates are the most complex compound data structure in PGP. And there is a test that explores how robust the certificate canonicalization is. For example, if you duplicate components or change the order of packets, stuff like that. Finally, there are some tests about ASCII armor. For example, I explore the question whether concatenated armored certificates are a keyring or not. And ASCII armor itself can be a source of brittleness. For example, you can have white space changes, or your armor text is quoted, or parts are missing, like the footer is missing, or finally, you can get arbitrary encoding done to your RMod block. So I check how implementations deal with that. Finally, the really bad news. Many implementations accept signatures from weak algorithms. So a third of implementations accept and successfully verify MD5 signatures. 5 of 9 signature implementations are fine with SHA-1 signatures. And 4 of 9 are happy with RIPE-MD signatures. And just for fun, I included a test that checks signatures over the shattered collision. And 5 of 9 implementations are fine with that. Okay. Next slide, please. So, I hope you consider interoperability testing important and want to join the effort. And I would like to invite you to do that. So if you want to add tests or propose tests, talk to me or open an issue. Most artifacts are generated on the fly using Sequoia, but some artifacts are just stored as test data. And if you generate artifacts, please use the common test keys, the Alice and Bob key. And if you want to get your implementation tested, that's really easy. You just need to implement the stateless Openpgp interface, and then we can plug it into the test suite. To do that, just talk to me. Finally, if you want to argue semantics, I wrote tests and then I thought about what the most useful outcome is, but I could be wrong, right? Again, please talk to me or open an issue, or let's take the discussion to the mailing list. Finally, if you want to run the test suite locally, that should be quite easy. Just clone it. Look into the README. There are some build dependencies you might need to install. Then you need to install the implementations you want to test, tweak your configuration, and then run it. And you can create both HTML output or a JSON output. And one area where help would be greatly appreciated would be in the presentation of results, because as we add more and more tests, the results become more and more unwieldy. So having a front end maybe that looks at the JSON data and then presents it in a nicer way, that would be very helpful. And that's it. Thank you.
Great, thanks. DKJ, go ahead.
Yeah, I just wanted to thank Justus for the presentation and for the tremendous amount of work that's gone into this. I think it's actually highlighted a lot of stuff, and I know that many bugs have been fixed as a result. We have a little bit of time for questions, but we're a little over time right now. Do folks have anything they want to raise? You can just put yourself in the queue by raising your hand. I want to encourage people to take a look at that. If you're in the working group and you have not looked at the interoper test suite, you're missing out. This is something that I think really makes it useful for implementers and for those of us who are working on the spec itself to get a sense of where things might be confused or confusing. So thank you, Justus. So our next presentation is about simple octet strings representing new elliptic curve points in Openpgp. Nibe, take it away.
Hello, hello. I'm Nibe. I have been working for GNU-PG implementations for years, and today I'd like to provide offer about SOS, simple octet string. currently, or it was 2019, I tried to implement support of ED448 and X448. And I found that GNU-PG is a kind of messy about ECC, especially for EDDSA. So, and I fixed GNU-PG when I introduced ED448 and X448. And it is currently available in GNU-PG 2.3 beta. And this presentation explained how I fixed GNU-PG. Next slide, please. Basically, SOS is a variant for MPI, multi-precision integer. Openpgp defines multi-precision integer, but for ECC, EC point is encoded into MPI. I think that that is the cause of many troubles. And for curves, which format is big endian, it is okay. But these days, modern ECC use little endian format. And because of that, we have zero removal problem, or any existing implementation which support ED25519 have to support zero recovery things. So currently the crypto refresh document will be introduce EDDSA in the next step, and you will see the problem. And next slide, please. The SOS definition is simple. It just changes the definition of MPI, and no semantics, but it is an opaque string. Because there is no semantics, we can avoid zero removal things. Next slide, please. Classic ECC, I mean, by the word classic ECC, I mean ECC of NIST curves or brain pool curves, big endian ECC. Existing specification for classic ECC can just replace the word MPI with SOS. Then it is compatible. So I think that it can be cleaner definition by using SOS definition. Next slide, please. Currently, in the RFC 6637, we have a definition of the encoding into MPI for EC point. But using SOS, we can just refer other specification, not inside Openpgp specification. Next slide, please. Now I use idea of SOS to support ED448 and X448 because new modern curves uses little endian format. SOS is better. I use SOS to represent scalars, scalars and EC point. Next slide, please. But currently, already many implementation of Openpgp adopted ED25519 and curve 25519. And ED25519 has been implemented before the idea of SOS, and it's a kind of mess. And curve 25519 key and encryption by ECDH was introduced by me into WinPG some years ago, and it's done before the specification of X25519 and the idea of SOS. So for those things, we need special care. Even if we don't use SOS, or even if we use SOS, because of existing data, we need care about corner cases. Next slide, please. Here is special things for EDDSA with ED25519. Somehow we invented the prefix 40 to represent an EC point. The prefix has been introduced to, the intention was to avoid zero removal problem. But unfortunately, the prefix was not used for the signature part of R. So here, zero removal problem is there. Yes. And because of that, implementation have to support zero recovery. Yes. So I don't like that. So for implementation in future, it's better to define or improve here. Yes. Next slide, please. And another special thing is curve 25519 ECDH. Here we also use the prefix for 0. But strange thing is that secret key is scalar represented as big endian MPI. And that's because of the when I implemented ECDH with curve 25519, specification of X25519 was not available. And to conform RFC 6637 idea, it has to be big endian. Yes. Next slide, please. And if I understand correctly, zero removal issues the causes historical things. There are culture of ASN.1, basic encoding rules, and DER. So those standards recommend or mandate zero removal, and some implementation like GNU-PG, because of this culture, it removes zero. Yes. And next slide, please. And the idea of SOS principle is that Openpgp format is to convey data of underlying crypto algorithm. And it is underlying algorithm which define the data format itself. And next slide, please. I explain 3 alternatives to SOS. At first, when I try to implement ED448 and X448, I was about to adopt easiest approach. It's basically following the ED2519 and the curve 2519. But I changed my mind because of these pros and cons. It was easiest for GNU-PG, but the all problem of zero removal or zero recovery things have to be there. So the complexity and providing vector, a test vector covering all the cases are quite complex. So
Nibe, we're running a little short on time. I apologize.
Yes, yes.
Yeah.
And next slide, please. So we have other approach, per curve approach, defining data format for each curves. Next slide, please. And the best one would be just a octet string. But it would require new algo number. Yes. And next slide, please. So my conclusion is that SOS is a compromise to introduce other modern curves of ECC without diverging from standard implementations. It's a bit strange, but backward compatibility is good. And that's my presentation. And basically, my point is that when we try to introduce EDDSA things into the standard, you will see problems. And I don't have a strong opinion to push SOS into specification, but we can share the experience of current EDDSA problems. Thank you. That's my presentation. And next slide is questions.
Thank you,
So I guess
Nibe.
we have, yeah, I guess we have not that much time. So Phil, if it's a quick comment or question, speed would be good. Thank you.
Yeah, I was just going to say there is another way that you can skin this cat, and that is the one that I do in UDF, which I dropped into the comments, where I use a random seed and a per algorithm key generation mechanism. It's defined for ed 25519 or whatever. They specify how to generate the key from random information. If we adopted that as the approach throughout the IETF, then you push the whole onus on all this part of tagging and bagging onto the creators of the new algorithms, and we don't need to revisit this, because the only things that the algorithm the code ever needs to deal with is the seed. So just a different way of looking at it.
Phil, that seems to me like that has pretty serious interoperability issues with deployed clients. I'm not sure how it actually applies to the elliptic curve representation that Nibe was talking about here.
Yeah, I mean, like, it doesn't solve your legacy thing, but it means that as you try and solve this problem, you're not building out a new problem for the next set of curves or whatever. It's a permanent solution.
So we are pretty close on time here. The session has, I think, 3 minutes left. Paul, I don't know whether you want to talk about any of the outstanding issues in the draft or about your plans for the next revision. But Nibe, thank you for the presentation.
Hi. So I'm not sure if there's any point in rushing through this, but just a generic thing for the people who haven't followed the list and who are now in the working group meeting here. What we've done is, as Daniel said in the beginning, we are pulling in a lot of changes in sizable chunks for people to reconfirm the consensus so that we can get to a state where everybody agrees on the BIS document. That is, for instance, Yoav, why you are seeing triple DES as a must algorithm, because we haven't gotten to the part where we're going to rewrite that section again. That is scheduled to be in the next or the second next update to the draft. So in general, I'm mostly interested in if people see if there's anything in the process that we can improve on so far. So we're basically trying to present this in little chunks with 1 or 2 weeks of time for the working group to give us feedback and then move on to the next one, in the hope that once we've consumed all the items that you see listed here, that we are basically in a similar position as the older BIS document, but we have confirmed all the consensus of all these items.
Great.
Please join by raising hands if you want to speak to that. But we can also follow up on the list if folks have suggestions about other ways to improve the process, like Paul is asking for.
And so the previous presentation is interesting in that it would have, if we would pull this into the BIS document, then we would have to see, because that would prevent that would help us in specifying some of the newer curves that we're about to merge in. We would have to do that in this newer way. So I'm just the editor of the document, so I would hope that the working group will at least discuss this SOS mechanism in the next 2 weeks, so that we can figure out how to incorporate that or not in the crypto refresh.
Great, thanks, Paul. And I guess the last topic we wanted to cover really was our assumption was that we'd have one or a couple of interim meetings, depending on the cadence of production of new drafts. I don't think there's too much to say about that here now, but just wanted to raise that that's the plan basically on how we think we'll be working between now and IETF 111. If anybody has who wouldn't otherwise be taking part wants to, they're more than welcome. We'll probably do some doodles and so on the list for dates and things quite shortly. I'm guessing we'll aim for 1 or 2 interims between now and July. And I think I just want to thank the presenters, and then I'll hand over to DKG, can close us out.
I think that covers it. I'm not sure I've got too much else. I'm hoping that we can get more people to give some feedback and proposed fixes on the list, and hopefully the editors will be able to drop a new revision in the next sometime in the next week once you've had a chance to recover from the IETF. So thanks everyone for coming, and we'll see you on the mailing list.
Thank you, and goodbye.